so we are going to start today picking up where we left off with the pre-recorded lectures. I was telling before I hit the record button, and I hope the content makes sense with the intersections, unions, and the definition of probability. Those are core concepts. I think overall the homework, in comparison to other finite courses I've taught, is fairly straightforward and easy, but you guys are just watching a video as opposed to sitting in a real class. So I worry about that, but there's not much I can do. Anyway, I'll stay after class if there's questions, that sort, but during class, I'm gonna have to move on to the new content. I will try to explain everything as thorough as I possibly can, but if you're stuck on anything from last week, stick around after class. I can help you. And then also look, be sure to watch those videos, okay? And, I post them on YouTube, and I do that for a few different reasons. One, I think the encoder is better out of the one that we have for IB Tech in-house. So I think it's a little bit clearer. And then you can also adjust the speed as well with YouTube. So for those kinds of things, I know that I personally have to speed it up. I can't just listen to someone drone on and on and on, even if it's myself, or especially if it's myself. So I always have to adjust the speed and go like twice as fast because I can't stand just listening to someone drone on and on. So feel free to do that. Okay, that's one of the reasons why I posted on that. So you have that availability. Or you could slow it down, hit it in reverse, however you take it, right? So that's the idea, right? I think it also makes a subtitles automatically. I think the algorithm or the Google makes the subtitles, so you might have that in case I mumble a few words, which I'm sure I do. Okay, but what we're going to do today is conditional probability. I can't even believe how much we're going to actually cover today. Luckily, each question is not overly in depth, but we will cover an insane amount of content. If this was a 16-week course, this would be like this would almost be 5 or 6 lectures, but hopefully it's not too bad when we actually get to it. So conditional probability. When we were doing this at IU, what we did was the class was flipped, and so this would be the beginning of the end of content that would have been on the midterm. So this would be some of the more difficult content that the students would see at IU. I think for you guys, it's going to be okay, though. I hope. We'll see how I explain it. I'm going to start with problem 2 in the homework to explain this concept, because I think that if we go over this problem and then go back, the first problem will make more sense to you. This is a topic, conditional probability is a topic that I cover in a lower level math course of mine. And I think that book does a pretty good job of explaining it, and it does it through these tables. So I think that might be a good place for us to start. That way we at least get our footing. Okay. But notice that we have this formula right here. This is the conditional probability formula. So the probability of event A occurring given B has occurred is the probability of A and B over the probability of B. So hopefully those each respective idea makes sense to you. The idea of A and B is something we went over last week, and the idea of what is probability of B is something we worked on before, but I think you'll be able to catch up even if you haven't seen that before. So let's find, where is A and B? What is this symbol here, this upside down U? this is like the word and, okay? So this is A and B. And what we're looking for is D given C, which is the formula D and C over the probability of C. Okay, so what is D and C? D and C from this table would be 0.05. That's where they line up in the table. So that's the probability of them occurring at the same time. What's the probability of C? Well, in this column, all of C is 0.2. So that looks like that would be a quarter. 5 20ths is 1/4. And in this problem, which you guys know just as well as I do, you got to watch how this online homework wants it answered. If we answer it as a fraction, it'll tell us it's wrong. So we got to be careful. Okay. So it's 25%. It's 0.25. It's rounded to 2 decimal places. The content from last time that we have to understand is this intersection symbol, this upside down U. So this was our intersection. That was like the word and, where we want what they have in common, what they, both of them occurring at the same time. Okay, so I want chips and the soda. I want both of them. Okay, what's the probability of me getting both of them? Then we'll talk about the union, which we talked about last week. Hopefully you saw, and that's like or. So one or the other or both. Stop me if you have any questions, or please, I have the chat pulled up if you have any questions, but I'm just going to continue to move on to the next question unless you have questions. So I have the chat pulled up in case there's anything on your mind. Okay. All right, so let's look at problem 1 from this. Find the conditional probability in a single roll of 2 fair 6-sided die that the sum is greater than 9, given that neither die is a 3. This, oh gosh. Okay, I want to make sure that I'm sharing the right screen. It looks like I am. Okay. Conditional probability. You have to think about that. We have 2 fair 6-sided die. You have to think about that. And the sum is greater than 9. We need to think about that. And what does it mean that neither die is a 3? This is most certainly the type of question that we see at IU, Indiana University, many times. Here you only have one of them. So let's take it apart. Conditional probability, recall, it's this formula. A, given that B has occurred, the probability of A and B occurring over the probability of B occurring. It turns out that you can also write this as the number of ways that A and B can occur over the number of ways B can occur. Since they have the same denominator, these are interchangeable. These are equivalent statements, okay? And I won't spend too much time in class proving that, but since they have the same denominator, we can interchange those formulas. That's really helpful because when you're going from problem to problem, one version might be more helpful than the other. Okay, but what are the events that are occurring? Well, we have the sum that is greater than 9. So the probability that the sum is larger than 9, given there's no 3s. Okay, given that no 3 has occurred. All right, well, with 2 die, they both have 6, 1 through 6, 1 through 6. How many sums can we get that are greater than 9? 2 dice. I don't know if you guys have ever, you play Candyland. I think Candyland has dice. Monopoly, any board game with 2 dice. And of course, there's gambling games too. But what numbers can the 2 dice sum to? All right, well, the smallest number that 2 dice can sum to is 2. You can get 1 and 1. and you can go all the way up to 12, 6 and 6. So that would be the largest sum that you can get with 2 die is 12, and the smallest one is 2, and you get everything in between. So in this version of the problem, we want the sum is greater than 9. So it could be a 10, it could be 11, or it could be a 12. Okay. How many ways can I roll a 10? How many ways can I roll a 10? Well, let's see. I could roll a, well, I can't roll a 1 and a 9 because there's no 9. I can't roll a 2 and an 8 because there's no 8. I can't roll a 3 and a 7 because there's no 7. But I could roll a 4 and a 6. That would give me a 10. I could roll 5 and 5. That would give me 10. Or I could roll a 6 and a 4. Those are possibilities. How can I roll an 11? Well, 4 and 8 doesn't work. 5 and 6 work. And 6 and 5 would work. And then with a 12, the only thing I could roll is double 6. So how many ways can that happen? 1, 2, 3, 4, 5, 6. Looks like there's 6 different ways I can roll a sum larger than 9. This one says neither die is a 3. It looks like I don't require that to happen. So how many ways can I get the sum to be larger than 9 and no 3s over the number of ways I can have no 3s? How many ways can that? So it looks like the numerator is the sum of 10, 11, and 12. 1, 2, 3, 4, 5, 6. So it looks like there's 6 different ways that can occur. Does that part make sense? Does it make sense how I found the sum is greater than 9? I get yes or no in the chat. I think that's the harder part of the problem. Does it make sense how I found 6 for the numerator? Okay, thank you, Jack. All right, next, how many ways can you not get a 3? How many ways can you not get a 3? So the number of ways, no 3s with 2 dice. For this, I mean, you can just count it, of course. I think it might be easier to count how many ways you can get a 3 and then just subtract it from the total. So there's 36 different choices, different rolls you can make. With 2 dice, 6 choices, 6 choices. 6 times 6 is 36. So there's 36 different rolls to be made with 2 dice. Now, how many involve 3? How many involve 3? Well, think about it. If the first one varies, but the second one is always a 3, 2, 3, 3, 3. How many do you have? Then you have 6, 3. Or you could have 3, 6. But let's go back. 2. All the way down to 3, 6. How many different ways can you get 3 rolled? I claim there's 11 ways to roll 3 because I'm not going to count 3, 3 twice. So I don't count them both being the same number twice. So I think there's 11 ways to get that. 11 ways to roll a 3. It means there's 25 in the sample space. 25. So I think the denominator is 25. So I think it's 6 over 25. I need to reduce that, but I don't think you can reduce that. So that would be my answer. The math is very, very, very simple. I mean, all I did was count. But understanding what do you count? What are you supposed to do for this problem? What formula do you use? Those are the difficult things about this. So please feel free to ask me any questions about that. If you have any questions about how I did that. There's different versions of the problem, and things that vary is the sum. You could have the sum is greater than 6. That doesn't involve 3 or something. You know, that those will vary, but the idea is the same. Okay. Are there any questions about that? Feel free to ask questions if you have questions. Let's see what number 3 brings. Here, number 3 is a table. Let's see what it's asking. It says, test the pair of events B and D for independence based on the following table. What does independence mean? We just celebrated 4th of July, but that's not in the sense that it means. So in probability theory, independence means something very, very, very specific. Okay? Independence means that the probability of A and B is equal to the probability of A times the probability of B. So we will see examples of independence, the idea of events being independent in probability theory. But this is the definition of independence in probability theory. It doesn't mean anything more or anything less than this formula. Okay. Since I've been helping students with finite in the past 10 years, one of the most common mistakes is that students will try to determine if events are independent just by a story problem, but not by the math. Okay. You need absolutely to go by the math and not by the story problem. Okay. So we want to quantify, are these independent, not assume or guess or anything like that. So hopefully that will be a lesson for you and you won't make the same mistake. All right. Now we want to know if the events of B and D are independent. If they are, then this formula would be true. So we need to test this as true or false. Is B and D equivalent to the probability of B times the probability of D? Okay, we need to see, is this true? Well, what is the probability of B and D? Because this is laid out in a table, we can just look. Looks like it's 12%. So that's 0.12. Okay, what is the probability of B? Probability of B is 0.4. What is the probability of D? Probability of D, 0.3. All right, well, 3 times 4 is 12. So there you have it. This is a true statement. And since this is true, then these events are independent. What does independence mean? In probability theory, it means that the probability of their intersection is equivalent to the product of the two events. That's what it means. So don't go by, it seems like these events would be independent. If you have a story problem, don't assume. You can test these things. How did I get the probability of D? I looked at the table, it said D, and then I just circled it. Nothing fancy. Jack, are you telling me I have something in the way? Oh, okay. Oh, the chat bar was blocking. Okay. Well, hopefully we can see. I just read it from the table. Didn't actually calculate. All right. Any other questions about that? Independence means it works with that formula. That is the definition of independent events. All right. Thank you for participating. Thank you for letting me know. Good problem 5 and see what it brings. Okay, number 5. A pointer is spun once on a circular spinner. Probability assigned to the pointer landing on a given integer 1 through 5 is given in the table on the right. Given the following events, complete parts A and B below. E is pointer lands on an even number. F, pointer lands on a number less than 4. What is the probability of F given E? Okay, so with part A, this part, what does that mean? This means the probability of F given E is the probability they happen at the same time over the probability of just E. I can exchange that if I need to with the number in the set. Because they have the same denominator, denominators reduce, I can exchange that depending on which one is the one I need. So I can exchange, I can go to either side and determine what it is I need. All right, anyway. So E is the pointer lands on an even number. So what is the set E? Okay, well, what are the even numbers? 2 and 4. Okay. What is F? F is the number is less than 4. So that's 1, 2, 3. So I think for this problem, we should look at the probabilities and not the number in the set. So I'm going to take this away. So we were given the probabilities. So do that one. All right. What are the numbers that they share? They share 2. Looks like they just share the number 2. So what is that probability? 0.1. Right? Now, what is the probability of E? That's 2 and 4. So that's 0.1 plus 0.3. 0.1 over 0.4. That's 1/4. This problem wants it as a decimal. There they have it. 0.25 would be the answer. Okay. Are these independent? Are they independent? Well, if they are independent, then E and F would be equivalent to E times F. That would have to be true. Let's see. The probability of E and F is the same as F and E. That's 0.1. We just found that a moment ago. Probability of E, just found a moment ago, which was 0.4. And the probability of F is, let's see, F is 1, 2, and 3. So that's 0.4. All right, that is not true. 0.4 times 0.4, 4 times 4 is 16, which is not 10. So this is false. Thus, E and F are not independent. Not. So I choose no. Questions on that one? In this problem, we saw that we could add the probabilities. Okay? We saw that when I wanted to find the probability of E, I just added the probabilities that made that set. I was able to add probabilities. And that's something you can do. You can add the probabilities of individual events to find a total event. And they should all add up to 1, right? Should. Probabilities 1 through, or 0 through 1. There can be a 0% chance something occurs. There can be 100% chance something occurs, but it has to be between 0. Look at 6. 6, we're looking at a tree. Okay, here's what we call in math a tree. Okay, think of heads or tails, right? If you flip a coin, you can either get heads, tails, heads, tails, heads, or tails. So this is the idea of a tree diagram. Very useful idea. The tree diagram is heavily used in mathematics. And the good thing about trees is that you can very quickly understand visually what's going on. And then they can also be easily translated into algorithms, for the most part, which can really be helpful if you're trying to program something. So if you're trying to program something in a computer process, you can use the idea of trees and then program that in to what might be happening in your particular program. So here it says compute the indicated probabilities by referring to the probability tree. First, we want to find the probability of M and S. Okay. What is the probability of M and S occurring? Well, where is M and S? So we have this event M, this event S occurring at the same time. So it looks like if we go down this track here, we have 0.3. And to get to S, they're telling us that that's 0.2. Well, 3 times 2 is 6. So this must be a 6% chance of occurring. And they tell us to write that as a decimal. So 0.06 would fit the bill there. That's the probability of M and S occurring. There was no conditional probability there, so that's helpful. Switch colors. Really quickly. All right, let's do the next one, which says, what is the probability of R occurring? Probability of R occurring. Well, where is R? It's like R occurs here and R occurs there as well. So there's two different ways I can end up at R. I could take the M track, M to R. I could go the N way, N to R. Two different ways to get the same spot. So that would be 0.3, 0.8, and going N, 0.7 times 0.1. This was my M route, N route. But the sum of those products, that's what's going to give me R together. Okay, well, that looks like that is 3 times 8 is 24, plus 7 is 31. And they want it as a decimal, not as a fraction, so I'm going to answer that one. So that's tree diagrams walking down. That wasn't conditional probability, which makes it a little bit easier. If it was conditional, it makes it more complicated, but here we didn't have to fight about it too bad. Okay, any questions about going down the tree and maybe why I added the R's together? Are there any questions like that? Look at 7. Fair coin is tossed twice. Consider the sample space of heads, 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 tails, tails, heads, tails, tails of equally likely simple events. Define the events as shown below for each pair of the events. Discuss whether they are independent, whether they are mutually exclusive, complete parts A and B. Okay, well, we'll get to the top. Yeah. So here this is kind of non-standard. So they're defining these events the way this problem is defining. Okay, it's not always going to be this, but they say E1 is ahead at first toss, and they want E4, which is ahead at second toss. You can draw a tree diagram to understand this. That's exactly what I'm going to do. So we're tossing a coin twice, heads or tails. What does that mean? 50% heads, 50% tails. And then after the first head, 50%, 50%. Okay? 50-50. 5, 0.5. So the probability of getting ahead on the first toss is 50%. Probability of ahead in the second toss, that's here and here. That occurs twice. Just like in the previous problem, we had R occurred twice. So how can I find the probability of event 4, which is ahead of the second one? Well, that's 0.5 and 0.5 plus 0.5 times 0.5. 5 times 5 is 25. And 25 cents plus 25 cents is 50 cents. I get the probability of event E4 is 50%. Are they independent? If they're independent, then they follow this formula. Probability E1 and E4 is equivalent to E1. And yeah, that turns out to be true, right? Because the probability of E1 and E4 is going to give us the same as if we go E1 times E4. So this is 0.25, 0. But that's true. So they're independent. So the reason they're independent is not because of the story problem, but because they follow that equation. Okay? That's all it means. That equation is either true or false. That's how we define independence in probability theory. That the probability of their intersection is also their product. They're not mutually exclusive because what? Look, it depends. They depend on each other in the first place. So they're not mutually exclusive, but they are independent. I found that E1 and E2, I followed the same path. E1 and E2 ended up being dependent because the formula did not work, and they are mutually exclusive. Are there any questions about part A? Any questions? Does it make sense how I got it? Does the tree make sense? Is there anything I need to mention again? I saved a picture of it in case you want to come back to it. The next problem I want to talk about is problem 11. I can't remember what I want to say about it. I remember I need to talk about it. Oh, I remember now. If the probability distribution of a random variable x is given in the table, what is the expected value of x? See, I can't believe we're already talking about expected value 40 minutes in, okay? Expected value would be like after, I think it was, there's 2 chapters in the previous book that we have to go over before we even get to expected value. The good thing is, it's actually not that complicated, okay? That's the good news. Expected value is not that bad. Let me try to prove that to you. So what is expected value? Expected value is kind of like an average concerning probabilities, okay? Let me think here. So what is the expected value of rolling a single 6-sided die? What would you expect to roll? If you roll 1 through 6, what would you expect to roll? If you just guessed, you might guess 3, right? You might guess 3. You might guess 4, okay? How can we determine what we would expect to roll given a single-sided die? Here's how you could calculate it. So 1 single-sided, no, not single-sided, single 6-sided die. What is the expected value? Well, what are the values? There's 1, and what is the chance of rolling a 1? 1/6. We have 2 times 1/6. 3 times 1/6. We have 4 times 1/6. We have 5 times 1/6. We have 6 times 1/6. All right. This is what we would expect to occur. Okay. What does that mean? Since they are equally likely outcomes, we have 1/6 plus the sum. This is what you would expect to roll. So just the sum, and you're going to get 3.5 is the expected outcome, the expected value of rolling a single-sided die. So it's right in between 3 and 4. If you roll a die, you can expect you're going to get between 3 and 4 for single-sided die. You can do the same thing for 2 dies. Okay, you can start at 1, 1, which is 2, and think of all the different ways you can get 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That's the idea of expected value. In this problem, it's way more abstract. It's way more abstract. In this problem, we just get some random x, and we're told the probability, and we're just finding the expected value of this random variable x. Okay, so what I do is I take my value and I multiply it by that probability. So what are my values? -3, 0.3, 3, 0.5, 5, 0.2. That's it. Let's see what we get. I think we get 1.6, but let's see. -3 times 0.3 plus 3 times 5 plus 5 times 0.2. 1.6. So in this abstract example here, we would expect the value of 1.6. Okay, that's the expected value. So expected value is the values times their probability. Sum all of those up. Okay, so it's the sum. I don't know if you've ever taken pre-calculus or calculus, but if you have, another way of writing this is sometimes we would write it this way. So that just means the sum. We just add them up. So we add up the products. That's the idea. Any questions, comments, or concerns about that question? We have some more examples. The next one I want to talk about. Let's at least look at problem 12 and see what it's talking about. I think it's a gambling question. Here we go. Number 12. You draw and keep a single bell from a hat that contains a $1 bill, $5 bill, $20 bill, and a $100 bill. What is the expected value of the game to you? Okay, so what can we expect? So we're going to draw something. What can we expect to draw? So these are the values. How many bills do we have? 1, 2, 3, 4. Looks like we have 4 bills. Okay, so what would be the expected value? What about the $1 bill? Okay. We have a 1. And what is the probability of drawing that 1? It's 1/4. What is the probability of drawing that 5? It's 1/4. Probability of drawing that 20. It's also 1/4. And what is the probability of drawing that 100? It's 1/4. Okay, so these are equally likely outcomes. So I can factor out the 1/4, and I'm just going to add bills there. And not all of the examples are the equally likely, but so far they have in these examples. At least with the die and this one. 1 plus 5 plus 20 plus 100. Oops. 126 over 4. 31.5. That is the expected value someone can think of, and they're going to play this game. Pretty low stakes. It doesn't look like there was any buy-in here, so that's kind of nice. That's the idea of expected value. You're taking the value times its probability, and you're just going down the line. Any questions about that? See what 13 brings. It's a similar but different. The unfair coin is flipped. If it's heads up, you win $1. If it's tails, you'll lose $1. The probability of heads is 43%. The probability of tail is 57%. Let X be the random variable for the amount won on a single play of the game. What is the expected value of the game? So we're looking for expected value, and that's how much money do we win. Let's break this down. They said the probability of a heads is 43%, and the probability of a tail is 57. Okay, so this is an unfair coin. This is a weighted coin. It's not 50-50. This is weighted, so we have to deal with that. If it's heads, we win $1. If it's tails, we lose $1. Okay, so how can we build this? Well, we can win $1. That's the value. What's the probability of winning that? 43%. And the other thing that can occur is we could lose $1. So I'll put a minus sign for the lose $1. Probability of that occurring, 57%. So, and what is 43 minus 57? 14. This is negative 14 cents. The negative sign in this formula is because of lose $1. That's where that negative sign is coming from. Normally, we don't have the negative sign. But in this example, we could lose $1. So I put the minus sign for negative $1. Questions? We probably need to do some of the problems with cards. If you haven't played with cards, playing cards in a while, it might be worth just looking up. There's a pretty nice Wikipedia page about card games. So just in case you haven't looked at cards in a while, there's a few things we need to know about them. So well, for instance, there's 52 cards in a deck. There's 4 suits in a deck, and there's 2 colors in a deck. You can have black, red. So that's the idea. So that means there's 4 of each type of card. That's the idea. So hopefully you've played with cards before. If you haven't, you're gonna have to look it up. There's a nice Wikipedia page with a pretty good picture of a deck of cards sprawled out that I've used before. So if you haven't played with cards in a while, take a moment. Hopefully you can still hear me. My computer just flickered. All right, let's take a look. Card is drawn from a 52 card deck. If it's a king, We win $30. Otherwise, we lose $2. What is the expected value of the game? Expected value of the game. First, we could win $30. That would be great. If we win $30, what's the probability of winning that $30? Well, that's if we get a king. What's the probability of a king? Probability of drawing a king, single draw. How many kings are in a deck? There's 4 of them out of 52. 4 cards out of 52 is our probability. So you can write 1/13 or 4 of 52. I'm going to leave it that way because I want to remember where that came from. What's next? Otherwise, we lose $2. Okay, so I'm going to put a minus sign for the lose $2. That's the other value that can occur. What is the probability of losing? Well, if I get a king, I win $30. How many kings were there? 4. So how many cards are left? There's 52 total. 4 are kings. So how many cards are not kings? A complement. How many are not kings? 48 are not kings. So that's the probability of not getting a king. From there, it's pretty simple arithmetic at that point. But that's the idea. Okay, so it wanted a decimal rounded to the nearest cent. So be sure you do that. That's it. But you might have to bone up on cards. Remember, there's 4 suits, 52 cards, 4 suits, 13 each suit of each type card, like king. There's 4 kings. There's 4 twos. So that might be worth recalling. The class doesn't overdo it with the cards. Different versions of the class. When I first started tutoring this class, it was very, very, very card heavy. And as time has went on, there's less and less card questions, probably because people play cards less and less. That is the idea. Any questions about expected value or anything like that I should cover? Got time for a few more before the break. $16 was kind of an interesting question. So let's talk about that one. I was kind of surprised that it's even on here. I don't think there's a show your work, so hopefully this will help you. A game has an expected value of $900. It costs $900 to play, but if you win, you get $100,000, including your $900 bet, for a net gain of $99,100. What is the probability of winning? Would you play this game? Discuss the factors that would influence your decision. I don't recall a problem like this on previous homeworks, but we can still do it. So they tell me the expected value. This is the part that surprised me. I saw this homework. They tell us the expected value. So I'm not solving for it. They're telling me. They're saying expected value is $900. Okay. What am I solving for? I'm solving for the probability of winning. Okay, so it's kind of like those previous problems, but backwards. They're telling me the expected value. They're asking me what is the probability of winning. So I have to pay $900 to play. And if I win, I make a net gain of 99,100. Okay, but I don't know what the probability of winning is. They don't tell me anything about that. As a matter of fact, they want me to solve for it. Okay, well, here's how I looked at this problem. I thought, okay, I know the expected value, and I know I would take whatever the value is times the probability. Okay, well, what's really going on? That would be the amount I win times the probability of winning. Plus the value of the other event, but in this case, that's losing. So I'm going to put minus sign. I could lose $900, and then that would be times the probability of lose. So this is how I was thinking of the problem. They tell me the expected value. They want me to find the probability of winning. Okay. I wasn't sure where they were going with this, but I knew that this had to be true. The next thought I had was, okay, well, the probability of losing is really just the complement of the probability of winning. So I don't know what each one is. But I know the probability of lose is 100% minus the probability of winning. That was my thought. So, okay, well, I mean, I've taught algebra for years, so my brain thought maybe I could build an algebra problem and I could just solve for it like a variable. And that's what I chose to do. So the $900 is the expected value. 100. I'm just going to write P as in the probability of winning minus 900 times, this is the probability of losing. I'm going to write 1 minus P. So I built an equation, single variable equation. One equation, one unknown. I should be able to solve this. And I am able to solve this. So 900. It's 100. P minus 900 plus 900 P. That's where I went with it. Okay. From there, I have 900 on left-hand side, negative 900 on the right-hand side. So that means I can add 900 to both sides. 1,800. And then on right-hand side, I have 99,100 plus 900. Well, I think that's just 100,000 started with. So 100,000 P's equals 1,800. So I guess P equals 1,800 for 100,000. It has a decimal. It's 0.018. Turned out to be correct. But I looked at this problem over the weekend. I had no idea where it was going with that. It doesn't have an example, but that's exactly how I thought about this problem. Is that, okay, well, this is what I know. This is what I want to know. Let's see where I can go with this. Now that you've seen it, it's probably fairly simple. You're just, in the end, you're just going to set up elementary algebra equation to solve. Are there any questions about how I knew what to do or what I got, that kind of thing? Any questions? That was number 16. Thought we should talk about it because that one was a little, I had to actually kind of think about that one. It wasn't a simple formula I could do. Take a peek at 17, and if there's time, we'll look at 19. 17, yeah. 5,000 tickets are sold at $1 each for a charity raffle. Tickets are to be drawn at random and monetary prizes awarded as follows. 1 prize of $700, 3 prizes of $200, 5 prizes of $20, 20 prizes of $5. What is the expected value of this raffle if you buy 1 ticket? And I'm thankful that they only want to deal with 1 ticket, as opposed to more than 1, which would make it more than enough complicated. All right, so it sounds like it costs $5 to play. That's one thing I noticed. I have prizes 700, 200, 20, and 5. So I think those are my values. We just want it for 1 ticket, so that's helpful. What is the expected value to win, to come away with after playing? So what's the biggest prize? The biggest prize is $700, but this person had to pay $1 to play. So there's 2 different ways we could set this up. One way is we could set this up where we have the values and then we subtract that $1 at the end because they had to play, right? Or we can subtract it now. And that's the way I'm going to set it up. So this person would really only make $699 because they paid $1 to play, right? Okay, well, what are the chances of winning that? That's 1 out of, for my numbers, 5,000. Those are my chances of winning there. All right, the next one is $200, but they paid $1 to play, so I think they only win $199. And there's 3 of those out of 5,000. Next one is $20. Again, they paid $1 to play, so that's 5 out of 5,000. And then we have the prize of $5, paid $1 to play, $25,000. And then from there, we could lose. We could just lose, right? Sad but true. So you could just lose your $1. And what is the probability of losing? Just losing the $1. Well, that would be the complement. Okay. So we have 1, 3, 5, 20. We have 29 winning tickets. So what does that mean? We have 4,971 tickets that just lose. They just lose. So there it is. There is my equation that I've set up. These are the values that they'll take home. And those are the probabilities. Hopefully it's clear how I got what I got. So I found the expected value is to lose 70 cents. I found that by playing this game, a player could expect to lose 70 cents after paying $1. That's the expected amount. How I got it. Any questions? The other way you could set it up, I think you could set it up where this is 700, this is 200, this is 20, this is 5. And then after that, you would have to subtract the dollar that they paid to play. But here it's just set up as the answer. So hopefully you find that straightforward. I got 5 minutes. That's enough time for another problem. I'm going to pick on problem 19. Decision analysis. After careful testing and analysis, the oil company is considering drilling in 2 different sites. It is estimated that site A will net 20 million if successful, probability of 40%, and lose 40 million if not, probability of 60%. Site B will net 80 million if successful, probability of 30%, and lose 8 million if not, probability 70%. Which site should the company choose according to the expected return of each site? So what are we trying to find? We're trying to find expected return. What is expected return? I would guess expected return is the same thing as that expected value. So I want to find the expected value of A and B, companies A and B. What is the expected value of A? Well, what are the values? A will get 20 million at 40%. So I just need to remember that these are in millions. So that's 20 at 40% and lose 4 million at 60%. So that's what I think A would expect to get. 20 times 0.4 plus 4 times 6. I'm sorry, minus. You get 5.6 million is the expected return. And then for company B, site B, 80 million with a probability of 30%. And they're going to lose 8 million with a probability of 70%. So what is their expected return? $18.4 million. So who would I choose? No, even though, famous last words, even though there's a 70% chance of losing, I'm going to pick B. Because that is the higher expected return. Higher risk, higher reward. Right, that is 6A. That's the idea. So you definitely have to understand last week to be able to do this. Conditional probability generally gives students trouble. Expected value is not too bad if you understand that kind of thing. And then because of the word problems, it can be tricky of what is it you're supposed to do for each problem. Hopefully it makes sense. Are there any questions about that? Any questions about the homework? Any questions about Distributional probability, expected value. Any questions? You guys are quiet today. Okay. Let's see. Got almost a quarter after. So I think now is a good time to take our break. So I'm gonna come back, since we're making good time, I'll come back at 2:30, continue, and we will be on our way. The next part is a little bit trickier, so we'll get into that. So, okay, I'll see you at 15 minutes at 2:30, okay? Hey, welcome back. Um, if you're back, could you write in the chat what state or country you're in right now? Maybe I'm in Indiana right now. So that way I know you're back. Makes sense. So I hope you're doing well. The weather's going well for you. I had a feeling that Brady was in Miami. Ethan might have been there too. Are you brothers? Yeah, I guess I shouldn't ask such questions. You don't have to answer if you don't want to. Are you twins? No, just brothers. Okay. I mean, I haven't seen a picture of you. I don't. Illinois. I'm from Springfield, Illinois. I don't know where you are. You're probably in the Chicago area. Maine, but city. When you say the city, are you saying you're in Chicago, the city? What do you mean, the city? Oh, yeah, Chicago. Yeah. Hey, if you're most people from Illinois are from Chicago. Yeah, anyway, so if you're here, please write what state or country you're in. Sounds like we're kind of spread out, but then we have some Indiana folks too. We have Wisconsin, another Illinois. Okay, so we talked about conditional probability, and there's probably 3 weeks worth of things I could talk about with conditional probability, but we're gonna kind of leave it there. We'll get the discussion there. Just it's a one meeting a week, 8-week summer course, so we don't have a lot of extra time to talk about extra things, but conditional probability stretches its application almost infinitely of its practicality. It's the more interesting of the probabilities that we've talked about. It's there's so many things you could study using conditional probability, not just gambling and games and things like that, but from logic, decision making, and that's pretty abstract. Finance. But the thing that keeps coming to my mind is that all of this material has kind of turned into the study of artificial intelligence. So most of what we study in this class has turned, at least since I've taught it, has turned into artificial intelligence, algorithms with social media, that kind of thing. So YouTube, Facebook, I would assume Instagram, certainly TikTok, any of the social medias that use some kind of algorithm to determine what they display. Amazon, Netflix to a somewhat lesser degree, but certainly Facebook, YouTube, and TikTok use algorithms immensely. And the way they do that is they figure out they take data on all users and they make data pools. And then they say, okay, well, this person has these features. Who else are they like? If they're like this person, then they probably like this content. And the idea is to get you, and to get me included, it works on me as well, to get you engaged as much as possible. And really, the only thing they have to do is implement this simple arithmetic formula, since it's proven true, this was developed in the 19th and early 20th century, probability theory. Because it's true, it very much works on human psychology, and it turns out that if you can develop a system that will make it more probable that someone is more interested in the next thing that occurs, they will be engaged for longer, even if they know that's going on. So even the developers, there's documentaries about it, there's books about it. Even the developers of the algorithm are not immune to the effects. So even if you know how this works, it's not one of those things where I can go, oh, well, now that you know how it works, you can see through it. Turns out, even if you know how it works, even if you developed it, it still works on you. So that's a pretty startling discovery that we've found in the past 10 years that is just basically multiplying and dividing. But it is certainly true with human psychology. So there's a couple things I want to bring up. I mean, I have no free time in this class, but I would be remiss to not bring up anything. One of the things I want to bring up is just I found an okay video that describes this process. This one talks about Netflix and Amazon, but things like Google, certainly anything dealing with Google uses this. Things that use just anything that can use this quote unquote algorithm to determine what you're going to be interested in. This is just a simple idea of movies. So, okay, this person liked Jurassic Park and the movie Airplane. Now you can probably determine what gender and what age they are just by those two movies. But if you have, say, how long they looked at the movie, how long did they did they watch the trailer? Just simple things like that. Did they watch the trailer and then watch the movie? Did they watch all of the movie? Did they break it up? Just by knowing all of that data, you can, of course, predict what they might like next because you have that data from all of the other of your customer pools. So here we just have 5 different movies, but that's the basic idea. And just from that, you can predict what people will like in the future. And then I know on Netflix, they have the feature, or is it a bug, where they even change the poster art for the movie. So you might be more likely to like The Matrix if it has this poster for The Matrix. So they have different posters that might be of more interest to you, or they might focus on one of the characters that you might be more interested in, or a more general poster. So your Netflix is going to look different to someone else's, even if it's on the same account, which is pretty bizarre. But that's the idea, and that's just Netflix. So one thing we've noticed, as a society, is that you can extend this not just what movies you might like, but what philosophies you might like, what political stance you might like, what diets you might be interested in learning more about. So it's not just entertainment. It could be, your whole social circle could be based on these algorithms. An example that's a little bit less frightening is one thing that I find interesting is all the math that went into early video games. It's easier to understand with the early video games. This is a really nice video. I'll put it in the announcement if you have any interest. This is what we're going to get into, and it's how they used different states to move from visual cues with the original Nintendo Entertainment Center system. So I thought I'll post that. It's just for fun. It's a quick, you can watch it or not. Don't watch it at all. It doesn't hurt my feelings. But it's kind of interesting how they use different states to predict what it should go into next. you know, as a math nerd, I find this kind of interesting. And since I grew up playing these kinds of video games, it's, you know, for me, it's kind of like um, double interesting because I actually understand the math now, and then I see how these things can work. Fairly simple, and a lot of these people that developed this really had to they had to be tricky because they didn't have a lot of resources. They didn't even have the same resources as this web browser had. So I think this person does a good job of explaining not only the simple math, but explaining how a program like this could work and function for a user that, you know, they wouldn't have to deal with the math. They can just enjoy the entertainment. So hopefully you can see part B. I'll post those resources if you have any interest at all. You can watch them, but those are just extra, just to go with it. And then there's a bunch of books I could suggest as well that go along with these ideas if you have interest in it. All right, so we're going to talk about state diagrams. Okay, state diagrams are of interest to us. It's a way of extending the idea of a tree. So if you have something like heads or tails, heads or tails, heads or tails, that's fairly simple. You have 50-50%. Okay, and each next step does not depend on the previous step. So getting the heads on the third roll, it doesn't matter. You know, it's not dependent on the second roll or anything. It's always the same. And because of that, it always being the same, you can extend this idea to just multiplication. Okay? You can just extend it to multiplication. We don't have to do the trees anymore, and we can turn this into a matrix. So you can turn this simply into probability matrix. And the good thing about that, turns out that if you turn it into a matrix, it's very easily computable. And because it's easily computable, it's very easy to use in programs, and thus it is easy to predict what a user might be of interest. Okay, this is how the original Google worked. Okay, so if you typed in hot dogs in the search, it had to guess, what do you want to see on the internet if you look up hot dogs? And what they found was the user would be more interested in hot dogs, that websites that are linked the most. So they would rank them. So that's how they found their Markov chain, which is what we're going to find now. Okay, so it's turning the tree diagram into a matrix, and since that's easily computable, it's of our great interest. So let's look at this diagram. This is just a general idea. So you have some initial state A. Okay, this could be anything. Maybe this is that you are in bush A. Sometimes I've seen it taught this way, that you can think of this as a bush and this is a bush. You have two bush, and you have a rabbit inside bush A. There's some probability that the rabbit will jump out and jump right back in to bush A. Okay, and then there's a probability that it'll move to the next bush. That's the idea. So they're in some initial state, they stay there, or they move to the next one. Okay, they either stay or they move. And this diagram is telling me what the probability of them staying or moving is. So if they're in the bush A, they'll stay in bush A with 90%. And we can turn this into a matrix, a probability matrix. So from A to A is 90%. From A to A is 90%. So if they're in bush A, they'll stay in bush A with 90%. They'll move to B with 10%. Okay, so there's the first row. There's only two states in this matrix, and there is the first row of my matrix. So if we're in bush B, the probability of staying in bush B in this example is 70%. So if we're in that state, the probability of staying in that state is 70%. And the probability of moving to the first one is 30%. That's the idea of taking this general idea, which is called a Markov chain, and converting it into a matrix. So this is also the idea of, it's really just a tree diagram, but we can extend it to a matrix since it's not changing. Okay, it's not changing. So the first part is to look at what we're given. This is my Markov chain. And I'm converting that into a matrix, a probability matrix. So if I'm in A, I stay in A with 90%, as told by the Markov chain. A to B is 10%, B to A is 30%, and B to B is 70%. You can also use this for business, and we'll see examples of that, of how this works for business and predicting if a business is going to be successful or a failure or a moderate success in the long-term future. So we can determine this. We can also determine where users might want to go. So in the future, where do they want to go? If they're looking up hot dogs, are they really interested in lunch places around the area? Maybe they're, anyway. So the first part is just converting the chain into a matrix. Then, what is this talking about? What is this S0? S0 is where we start. That's the starting position. That's like the spawn point. That's where we're starting, okay? So it's saying it's starting at 0.2, there's 20% chance we're in bush A, there's 80% chance we're in bush B, okay? So even where we start is not told to us. There's just a percentage of we're in bush A or in bush B. They want us to find what is, after a transition, what is the probability of being in bush A or bush B? And what we have to do to calculate that is to get the first initial state, or the state after we started, is we take where we started times the transition matrix. Okay, so I'm just going to multiply where I started times the transition matrix, and that'll tell me the probability of being bush A or bush B after one transition. So let's do that. Okay, so 0.2, 0.8, and we're going to multiply that by the transition matrix that we were given through diagram. Hopefully, we can review and recall how it was that we did matrix multiplication. Okay, so remember that you go row times column. Remember that you have dimensions of 1 by 2, 2 by 2, and this is going to output a 1 by 2. So we're going to get two numbers when we're done with this operation. So what is that? That's 0.2 times 0.9. That's 18 plus what? Plus 24. 18 and 24 is 42. So I think that's 42%. Right. First row, second column, 0.2 times 0.1, that's just 2. And then 0.8 times 0.7, that's 0.56. So 56 plus 2 is 58. So that, after one transition, is the probability of it being in bush A or bush B. 42% of being in A, 58% of being in B. So more likely of being in B. S2 is just this process once again. So we just want to know what is it after two transitions, where are we? Where are we? Okay, so how do you find that? Well, S2 is S1 times the transition matrix, and we just found what S1 was. So that's 0.42, 0.58, 0.9, 0.3, 0.1, 0.7. And this one gets a little, I mean, the arithmetic is fine, but it's a little bit harder for me to do in my head. So I'm going to get by 2, 0.42 times 0.9 plus 0.58 times 0.3, 0.552. And then we need to do row by column, so 0.42 times 0.1 plus 0.58 times 0.7, 0.448. So that is S2. After two transitions, that's the probability of being in bush A or bush B. But there's a lot of information in one example. There's a lot. So we're taking almost everything we've learned in the class and condensing it down into one problem. So we're going all of the matrix math we've learned and all of this probability we've been working on. And now we're down to a single problem where we're talking about Markov chains. And that's exactly how the original Facebook worked way back when. You probably weren't alive. I was just a kid when two math students figured this out. But it turns out it is extremely useful to predict what people want, even if they themselves don't know what they want. All right. Is there any questions about the mathematics that I can answer? Is there any part you would like to see again? Is there any step that I should talk about again? Anything I should say again? So one thing about this type of math, I talked about it's very easily computable. What on earth does that mean? It means it's real easy for a computer to spit out the answer. And if that being the case, then that means it should be pretty easy for me to plug this in a calculator and get an answer. Okay. So the next thing I want to do is I want to show you how I can plug this in a calculator and just spit out the answer. So I'm going to redo the problem, but now I'm going to use calculator. Okay, so I have my PI83 plugged here. And I'm going to try to calculate this problem. The way I'm going to do that is I'm going to go to matrix. So I go to matrix, I'm going to edit, and I'm going to make A my probability matrix here. Okay, so that's a 2 by 2. So I need a 2 by 2. 0.9, 0.1, 0.3, 0.7. Okay, so A is my probability matrix. Now I'm going to set up this state vector here. I'll let that be B. And that, oops, edit. Okay, so that's a 1 by 2. And where did we start? We started at 0.2, 0.8. Okay, here we go. I can have the calculator find this for me. So I can go to matrix B. So matrix B times matrix A And it gives me right there, computed that for me, just directly. I claim I can actually go skip steps. I can go from this initial vector all the way to the second one. I don't have to go step by step, especially if I have a calculator. So let me show you how that works. So I have my matrix, my vector where it started. I can times that by the transition matrix. So that's one transition times another transition. That's two transitions. So that's the initial state vector times P, and that gives me the second one. And you could imagine if I can skip from 0 to 2, I could probably also skip to as far as you want to skip to. Within reason, I could probably skip to 100 steps and not just 2. So it's very easily computable. Computers are very good with matrices. So this is easy to find by hand and even easier to use a calculator. So that's how you can use TI-83. I might go to another example and I can show you on Desmos how you can do this as well. Okay. So I want to kind of explain everything all at once. Warning, you have taken no action. I want to take action. Okay, let's look at problem 2 and see what we've. Okay, problem 2, use the transition diagram shown on the right to find S1, S2 in the initial state is 0, 0, 1. Fine with me. Okay, so what is the transition matrix? We want to find the transition matrix. So that's P. From A to A, we find it's 0.3. From A to B, we find 0.3. From B to C, we find 0.4. Now we have 3 bushes. Note that these sum to 1. They have to. Okay. Something's got to happen. Something has to happen. So those add up to 1, right? Okay, now let's talk about B. All right, from B to A, looks like I have 0.2. B to B, I have 0.7. And from B to C, I have 0.1. And then C to A, 0.4. C to B, 0.2. C to C, 0.4. And that should add up to 1. 0.4 plus 0.2, 0.6 plus another 4 gives me 1. Okay, so there is my transition matrix diagram. Let's see if we can find the position after the first transition. Now, in my example, they tell me this is my starting value. That's my starting value. So I need to take that and multiply it. Okay. So that's 0, 0, 1. Row by column. Row by column. 0 plus 0 plus 0.4. 0, 4, 0 plus 0 plus 0, 2, 0 plus 0 plus 0. There's the first transition. That's the idea. That's the idea. Okay. Do we need to find the next transition? Yes, we do. So let's do that. After we found the first transition, we can find the second one. S2 equals S1 times P. We just found S1, so 0 0.4, 0 0.2, 0 0.4. And this is a 1 by 2. This is a 2 by 2. So what do we get? Row by column, row by column, row by column. Row by column. So 0.4 times 0.3 plus 0.2 times 0.2 plus 0.4 times 0.4. Got 0.32. Point 0.4 times 0.3. It's 0.2 times 0.7 plus 0.4 times 2. 0.34. Oh, 0.4 times 0.4 plus 0.2 times 0.1 plus 0.4 times 0.4, 0.34. We have it. There's the second transition. So we think it's 32% after two transitions, they'd be in bush 1 or state 1, A, I should say. 34% chance they would be in state B, 34% chance they would be in state C, and those have to add up to 1. That's the idea. Right, now I think I answered all of the parts. Yes, I did. Okay, from there, that's roughly doing it by hand. I did some of the arithmetic using my Casio calculator there. I want to show you can do this same process, and I just showed TI-83. So how about I show how you could do it in Desmos? Desmos also has an calculator, and it's even better. So let's take a look. Okay. I have it here somewhere. So I looked up, I Googled matrix calculator, and there's many choices. There's a lot of choices for matrix calculator. I'm going to choose Desmos as my preferred online calculator. And I need a new matrix. So I'm going to set up a new matrix. I think this was a 3 by 3. Check. Yeah. So what are our entries are 0.3. Oops. It's not quite what I wanted. 0.3, 0.3, 0.4, 0.2, 0.7, 1, 0.4, 0.2, 0.4. Okay, there's A. My state vector, it's the new matrix, was 0, 0, 1. All right, just to show you, you can skip steps using matrices. When you go B times A times A, and we would be able, already it's telling you the answer. There is our second transition right there. So it's telling me, and this one's even nice enough. You can switch back and forth to fractions, if you please. Okay, so that's pretty cool. Like I say, this stuff is easily computable, easily computable. So you can use that as well on your homework, speed things up a little bit. Any questions, comments, concerns, criticisms about those first two? The good thing is most of the homework is just like this. So the bad thing is it might be complicated. The good thing is it's really going to be a lot of repetition. It's not going to be too terrible. All right, I'll skim problem 3 and then we'll work 5. So number 3, it says, is there a unique way of filling in the missing probabilities in the transition diagram shown? If so, complete the transition. All right, so note that with this, we have a missing piece here and a missing piece here. But I know that they have to sum to 1, right? So 0.3 plus something equals 1. And 0.9 plus question mark equals 1. So it's pretty easy to see, okay, I can figure out what those have to be. Be 0.7, 0.1, and then from there, you just find that transition matrix. So it's not too bad. You just kind of have to know what you're thinking. I hope it's clear. It's clear. Number 5, Markov chain has 3 states, A, B, and C. The probability of going from state A to state B in one trial is 20%. This could vary between our problems. And there's so much information. What I personally did was I actually I wrote down the matrix before I even did the Markov chain just to kind of piece it together for myself. So it's telling me I have 3. So I know I have a 3 by 3 there. It says from A to B is 20%. A to C is 0.3. B to B is 1. That means that has to be 0. And going from C to A is 20%. And C to C is 60%. All right, 6 and 2 is 8. So we know that has to be another 2. 3, 4, 5. So this has to be 50%. So I filled out the matrix myself before I did the Markov chain. And I found that this would be the Markov chain diagram. It worked for me, but that is probably randomized. So be careful. It might not be D for you, but the idea should be the same. Okay. Then from there, let's see if I can switch to the mouse. From there, I just filled in my Markov chain. Just remember that, write that variable. Rows sum to 1. So that's how I knew, okay, if B to B is 1, everything else has to be 0 because this adds up to 1. If C to C is 0.6 and C to A is 0.2, okay, well then C to B has to be 0.2 and so on. Because I know rows have to equal 1. You can think, 100% something happens. Something has to happen. Hopefully that's clear enough. There wasn't much computation to be done for that question. Just had to understand what they were asking. I can't remember what problem 6 brought me, but it didn't bring me too much trouble. Find the probability from state C to A in 3 trials given the transition matrix of powers of P below. We have P p squared, and p cubed. Probability of going from state C to A in 3 trials. They pretty much give me the answer right there. C to A. It's right there. It might randomize what we're looking for, but that's the idea. That is the idea. Not much to compute that time. But hey, that's not something to complain about, I suppose. All right, let's look at number 7. There is a lot to compute in this one. Okay, and if you have any interest, I solved this problem by hand in my notes, which my notes will be posted after class. But I have a feeling you don't want to do that. You can, and I will explain how you do it, but I'm going to guess you don't want to do it. And in case you don't want to, we can very easily compute this using the calculator. So it wants P4. All right, well, how can I calculate that? The old way, the way back when we had to do this by hand, you would go P by P gives you P squared. So I would do that by hand, and I would find P squared. Then to find P to the 4th, I would go P squared times P squared gives me P to the 4th. So that's how I calculate this by hand, and then I would actually do it. What is P times P? 0.6, 0.4, 0.5, 0.5 times 0.6, 4, 0.5, 0.5. So by hand, I would find that. That's P squared. Whatever I get, I multiply that against itself, and that gives me P to the 4th. But since we're allowed calculators in this class, we might as well use the calculator to do this. Since it's so laborious by hand, and it's absolutely nothing by a calculator, I'll just show you how to do it with calculator. The other thing we want to find is the 4th transition. Where are we? So S4 is the starting point, the spawn point, S naught times P to the 4th. After 4 transitions, where are we? So again, you can do that by hand, which if you look at my notes, you'll see how I did it. Or you can just use the calculator. That's all. Okay, so let me pull that calculator up. Here we are. And I need some new matrices. New matrix. This is a 2 by 2, yeah. So 0.6, 0.6, oh, sorry, 0.4, 0.5, 0.5. And we go just simply C to the 4th. And it tells me 4 transition matrix is right there. Great. Let's come up with a vector here, new matrix. On 1 row. I start 50-50. 5.5 D times C. And there's very easily computable by hand. It's a little bit laborious, but it's the same idea. I hope you don't feel cheated by me showing you how to do it on the calculator. You can do both. If you want to do it by hand, you are more than welcome to do it. That's how I did it in my notes. But you can also use a calculator. And since the arithmetic is so much, it can be kind of nice to be able to check our answers. So please stop me if there's any questions. If not, let's see what, got about half hour left. So I think we can look at problem 8 and see what it brings to the discussion. A television campaign is conducted during the football season to promote a well-known brand X shaving cream. For each of the several weeks, a survey is made and has found that each week 90% of those using brand X continue to use it and 10% switch to another brand. It is also found that those not using brand X, 10% switch to brand X, and the other 90% continue using the other brand. So we want to find what is the Markov transition diagram. I'm trying to find the diagram. So this is X and not X, I guess. We could use A and B. I'll just use X and not X. How about that? Okay. They say for each of the several weeks, a survey is made, and 90% of those using X continue to use it. So from X to X is 0.9. And that means this has to be 10%. Since that was 0.9, has to be 10. Okay. Then we have not X to not X, and not X to X. It says not using brand X, 10% switch to X, 0.1. So we know that 90% stay with the brand they're using. So there's my diagram. Finding the transition matrix is very easy once we've already have the diagram set up. We have 0.9, 0.1, and 0.9, 0.1. There's my transition matrix. Yeah. Part C, if 30% of people are using brand X at the start, what percent will be using it 1 week later, 2 weeks later? What does that mean? Well, it sounds like they gave me the initial state. They said 30% are starting with X. Why did I write the number 2? So that's 70%. So there's my initial state right there. They want it after 1 week, after 2 weeks. So we can just multiply that times our transition matrix, find it, and then we can take that and multiply it against our transition matrix. Okay. Since I feel guilty, I've used the calculator a lot. We can, of course, put that in the calculator. I'm going to try to do this by hand. It's easy enough. That way we can recall what these steps are. So to find, let's see, to find, show both. It's getting kind of crowded. P. Okay, so we want to find S1. S1 equals starting point times the transition matrix. They told me it was 30% are starting with brand X, so that means 70% are not on brand X. 0.9, 0.1, 0.1, 0.9. What are they looking for? They said the percentage of people using brand X 1 week after. So they want this value right here. I'll have to find both anyway, but that's what the value is looking for. So let's find it. Row by column. Row by column. Okay. That means 0.3 times 0.9 plus 0.7 times 0.1 is 34%. 0.34. Might as well find the other one. Well, we know it's the complement. I can just take it from 1, or I can do row by column. Either way, it should be 66%. All right, now they say what happens after 2 weeks. Okay, so I can take S1 times P, and that gives me the second transition. So let's do that. 0.9, 0.1, 0.9. All right, let's see what happens. So 0.34 times 0.9 plus 0.66 times 0.1. I get 0.372. Then we just need the complement of that. So from 1, go, but they just want to just mark it. So 37.2%. We can, of course, calculate all of that by hand or all of that using a basic calculator like I did, or you can use a matrix calculator to do it. But that's how I would set it up. That's what it means. I also claim one more thing. I claim that we could have skipped all the way down here if we needed to. Okay, if there was a question that made you skip all the way to the second one, you can go S naught times P squared gives you the second transition state. That's the idea. It didn't ask me to do that, but if it did, I can do that. I can do things like that. Okay. I would imagine this is confusing. I don't know. I have no feedback. Is it making sense? From a scale of 0 to 10, 0, this doesn't make any sense at all. 10, this makes perfect sense. I have no questions. Can you give me a feedback where we are? 0, this doesn't make any sense. 10, this makes perfect sense. How are we doing? It won't hurt my feeling. If you put a 0, it doesn't hurt my feelings. I just want a feedback of how we're doing. I would think this is confusing. If you've never seen this before, which I assume you haven't, I would think it would be confusing, but numbers are high. All right. So, the good thing about it, I guess, especially from your point of view, is that it's easy to program into a calculator. So you can get answers quick, right? That's nice, right? When they talk about probability generally, that can be confusing. That can be hard because you might not even know where to start. That's what makes it hard. This stuff, if you kind of get an idea of what's going on, it's not, it's kind of plug and chug if you've got the calculator. And you guys are allowed to use a calculator, so you might as well. I think this one was same old, same old. I want to kind of focus on the word problems. Find SP. The only thing I think was confusing about this one was the SP, but I'll just describe what I did because I think if what made sense before, this is nothing. Okay. So they gave me matrix P, and they gave me it somewhere to start, 0, 1. They asked me to find S2, S4, and S8. If you're going to use a calculator, what you can do is you can take S naught and times that by P squared. And that gives you S2. Right? You can also go S naught times P to the 4th. That gives you S to the 4th. Or you can take S naught P to the 8th. That gives you S to the 8th. Okay, after 8 transitions. By hand, what we used to have to do back in my day, what we used to have to do is we would have to go P times P gives me P squared. Then P squared times P squared gives me P to the 4th. P to the 4th times p to the fourth equals p to the eighth. Now, when I was undergrad, we had to do that by hand, no calculators, and do it correctly. Not just do it, but do it correctly, all within a timed test. So it was pretty brutal. So, be thankful you can use calculators, because you don't get much out of doing it by hand. It's just arithmetic, but it is tedious and it's very easy to make a mistake. Anyway, so there's your transition matrix. The only thing I wanted to show, it's going to have you do it again and again with different starting points. Okay, that's not that big a deal. And then one's talking about with SP, they're talking about long term. Okay, so can you decide what this is going to do long term? So after two transitions, I see, okay, it's 13%, 14, a little over 14, a little bit more over 14. So they're saying, okay, as it goes, can you see where this is going? Notice 87, 85, 85. Where is this thing going towards? Okay. After 9 transitions, after 18 transitions, where's this thing going to? Well, it actually goes down to it kind of levels off. Okay, that's the idea. It levels off. These are called regular Markov chains. When that occurs, what they do is they just kind of go down to a point. Almost, if you're taking calculus, they go down to a limit. You can think of that. I'm trying to find where it says SP. Yeah, so you can see you're just rounding it to 3 decimals. You can see where it goes towards after you do these transitions. So S, it's just going to go down to this point here. Okay. So where is it going towards? It just round to 3 decimal places. So it's pretty easy to do in a calculator. That was the only thing I wanted to say about 9. I had some comments about 13. Flip through 10 and see what you get. That's pretty easy. Could this be regular? To find if it's regular, so regular Markov chain means that P times P times P times P to the K has all positive entries with no zeros. Okay. So if you multiply this thing against itself many, 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 many times, do the zeros go away or are all the entries positive? That's the idea. Okay. So this one, you could just take your matrix, go P. When we did this by hand, we usually said you would know for sure by the 16th. So if you go P to the 16th, you know pretty well if this is going to be regular or not. If all the entries are positive, there's no zeros. Everything has a positive entry. What would it be? That would tell you if it's regular. If you're using a calculator, this is totally trivial. But by hand, it's still not too bad, at least with 2 by 2. 4 by 4 is a little bit trickier. All right, where are we? About 330. Okay. Approximate the stationary matrix S for the transition matrix P by computing powers of the transition matrix P. What on earth are they talking about now? Stationary matrix. So this is in the long term. In the long term, where is this going? And since this used to be kind of a business class, the idea was if you started somewhere, if a business started in some state, where is that business going to go in the long term? we could say, is it going to be a failing business, a moderate business, or a high success business? And that's the idea. So you can look at this in the long term and see how this goes. And it comes with an equation. There's some vector S times the transition matrix, which ends up being S. It ends up being itself. We want to solve for what that matrix or what that vector is. Okay, so let's do that. All right. I'm going to call it just X and Y. It's two different numbers. And it's multiplied by this matrix given. That equals the same X and Y. This is after the long term, after many, 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 many transitions. Where does this thing end up? That's the idea. So we saw in that example that eventually it just kind of trails off. And yeah, down, way down there, the decimal points, they change a little bit, but not too much. Well, we can say, okay, way down the line, where is this thing going to end up? Well, we can find that very easy just using this equation. So how I'm going to do this, I'm going to row by column, 0.47 x plus 0.19 y equals this x right here. So we're kind of thinking about, remember our rows and columns, they're matrix algebra. We have 0.53 x plus 0.81 y equals y, this y. All right, two equations, two unknowns. Now I have x's on both sides, so I'm going to subtract, and that gives me 0.53. That's negative 53 x plus 0.19 y equals 0. 0.53 x minus 0.19 y equals 0. Two equations, two unknowns. We want to solve. Okay. Note, these are the same equation. That's the same equation. They're just a change in sign. Okay. So they're very related. So if I solve it just going from that, I won't get any information that's helpful because that's the same equation. These variables are dependent of each other. So what can I do? I need to add in the idea that x plus y equals 100%. Okay, if you add these two numbers together, they have to equal 100%. Something has to happen. One of them could be 0, that's fine. But if you add them together, they have to be 100%. So I need to add that information in. So I can pick my favorite one out of those two. How about this one? I'll pick this one as my favorite. And I'll add in this normalization here, that if you add them together, it equals 1. And then I can solve 0.53 x minus those are the two equations, two unknowns I want to use to solve this. Now we just need to solve for two variables, two equations, and we've been working on that since I think the first time we met. So we've done that lots. Let's just use a calculator to do it. That's the easiest way because we just want to solve for what is x and what is y. So I'm just going to use my calculator to do that. I can use Desmos, I can use this, and of course I could even use substitution if I want. I'm going to choose to use a calculator. 2 by 3. 0.53. Negative 0.19. 0. 1. 1. Okay, now I want the calculator to use this. Matrix, math, reduce row echelon form. I want you to do that with matrix. There it is. There are my entries. So in the long term, we find this. In the long term, that's the probability. If you're just going failing business, successful business, those are your probabilities. Okay. But chances are in reality you have more than 2 variables. But that's the idea. Any questions how I got there? Each step is fairly easy to do, but there's a lot of steps. Are there any questions of how I got there? Are there any questions of why I added x plus y equals 1? That was problem 13. Got about a little over 10 minutes. Let's see what, is it 16 or 17? Let's talk about 16. If there's time, we'll talk about 17. Okay, a red urn contains 3 red marbles, 2 blue marbles, and a blue urn contains 4 red, 1 blue. A marble is selected from the urn and the color is noted and the marble is returned to the urn from which it was drawn. The next marble is drawn from the urn whose color is the same marble just drawn. Thus is a Markov process with 2 states, which are drawn from red or drawn blue, complete A and B. What can I say? We have red. We have blue. Diagram going. Okay. Let's see. The red one has 3 red and 2 blue. So the red is 3 out of 5. And this would be 2 out of 5. And the blue is 4 red. So that's 4 out of 5. 1 out. And of course, 1 out of 5 is 20%. 4 out of 5 is 80%. So that's pretty easy to do. Let's see which diagram would work best for us. I think this one is the clear choice. Even though it's not fractions, it's decimals, the idea is there. So I think that would be the best choice for our diagram. So even though it looks like, it's from last week's material, still can do that. All right, write a transition matrix. If we can make the diagram, it's pretty easy to make the transition matrix. So yeah, from red to red, we have 3/5. 60%. Red to blue, 2/5 for 40%. Blue to blue is 20%, 1/5, and then 80% is a half. So there you are. There's your transition matrix. Was there a second, third part? Oh yeah, there is. Find the stationary matrix. Okay, stationary matrix is in the long term, where is this going? In the long term, where does this go? So the stationary matrix is S times P equals S. X, Y times my matrix there, 0.6, 0.4, 8, 2, and those entries S, Y. Okay, now that means I have 0.6x plus 0.8y equals x, 0.4x, 0.2y equals y. Two equations, two unknowns, but we can rewrite this. It's negative 0.4x plus 8.8y equals 0, and 0.4x plus negative 0. And those are the same equation as we predicted. Two equations, two unknowns, but they're the same equation. So it's really one equation, two unknowns. We need to add in normalization. We need to normalize, which means that x plus y equals 1. That will normalize this.
Where is the negative coming from?
From here to here, is that what the question is?
Yeah.
Yeah, so I have 1x here. Thank you for asking. I have 1x here, I have 0.6 here, so that would be 1x minus 0.6, x equals negative 0.4x. Whoops, and I hit something here. Does that make sense? I don't think I explained it well.
Yeah, that does. Thanks.
So I'm just moving everything to the left-hand side, and that's where the negative. So then I add in x plus y equals 1, and then I can just reduce the matrix. EF 1, 1, 1, 0.4, negative 0.8, 0. Gives me 1, 0, 0, 1, 0.6 repeating, 0.3 repeating. That's how we get it. Good question. Any other questions? I'm sure somebody has another question. Other questions like that? I have a note on. I think I want to look at 18 in my remaining time. Can't remember the details, but I remember there was something funny with it. Let's look at this with our remaining time. So an auto insurance company classifies its customers in 3 categories: poor, satisfactory, or preferred. Each 5% of those in the poor category are moved to satisfactory, and 10% of those in satisfactory category are moved to preferred. Also 10% in preferred category are moved to satisfactory category, and 10% of those in the satisfactory category are moved to the poor category, customers are never moved from poor to preferred or conversely in a single year. Assuming that these percentages remain valid over a long time, how many customers can a company expect to have in each category in the long run? Sounds like I'm looking for long term. So it seems like I'm going S times P equals S. I got to find out the details of that. But that seems what I'm looking for. Okay. Let's see if we can find that transition matrix. It's given in a sort of complicated, messy way. Let's see if I can figure out what's going on here. Got this correct. I'm happy I got it correct. I don't need you to tell me. Anyway. Let's see, poor, satisfactory, and preferred. 5% of those in the poor category are moved to satisfactory. So that would be 0.05. 10% of those in the satisfactory are moved to preferred. 10% in the preferred are moved to satisfactory. 10% of those in the satisfactory are moved to poor. Customers are never moved from poor to preferred. Or conversely. So it doesn't sound like you never go from, if I read that right, you never go from preferred to poor. Customers are never moved from poor to preferred or conversely. So it sounds like that is a 0. And it doesn't give us the rest, so we have to assume if this is 5, if this has to add to 1, that's 5, so this would be 95. Row 2, we have 1 and 1, so this has to be an 8, and this would have to be a 9. Let me double check and see if I agree with myself. I think that's what I read. 0.1.8.1, 0.1. Yeah, that's right. All right. Now we want to find what's the long term. So that's going to be some X, some Y, some Z times this transition matrix. That equals X, Y, Z. Okay. So from there, we have 0.95x plus 0.1y plus 0 equals x, 0.05x, 0.8y, 0.1z equals y, and 0, 0.1y, 0.9z equals z. But we also need to add in x plus y plus z equals 1. We have to normalize it. So from there, we have to do the same step we did before. We have to subtract both sides. So we need to get all the variables on the same side. So it's negative 0.05, 0.1, 0, 0, 0.05, negative 0.2, 0.1, 0, and then I can just add in my normalization. And reduce that matrix, and it'll give me my long term. Okay, it'll give me my So that's my time. I tried to get as many examples as I possibly could without going too fast. Stick around if you have questions. That's it for this week. Don't forget you have week 5 to do. It's a fairly quick homework, especially as far as this class goes. It looked like a lot of homework times were cut in half when I was peeking. It looks like you guys are doing good, but reach out if you're stuck. Okay, I'll stick around after class if there's questions. I wish you well, and don't hesitate to email me if you have any questions, okay? All right, have a good week. Stop.